Alright, today we continue the story of point particle action by adding the electromagnetic interaction, the electromagnetic charge. So last time we studied the action for a free particle, and we saw that it moves on a straight line. Now we want to consider the case in which the particle is charged and it is moving in some background electromagnetic wave. Sorry, not wave, some background electromagnetic field. And we want to derive the relativistic equation of motion for a charged particle. After finishing this, then I will talk about symmetries and another theorem and conservation laws. Yeah, that's the agenda for today. Okay, so what did we have yesterday? We wrote the action for the. We consider a particle that moves along some trajectory, which we parameterized it by sigma. So it goes from point A to point B along some trajectory. And then this trajectory we call the x mu of sigma, where sigma we took it to run from 0 to 1, so at 0, sigma equal to 0, we are at this point, d1, x1. So here I'm just drawing a diagram for a two-dimensional or 1 plus 1 dimensional space-time, but everything is general. So x mu of 0 is x1 mu, and x mu of 1 is x2 mu. And then the action that we wrote was just the Lorentzian length associated to this path. So S of this x mu of sigma for this path was basically what we define as the Lorentzian length, which is just dividing this into little pieces and adding up the Lorentz invariant element of length or time, proper time. So if this is an observer, that action is really what the clock of that observer is measuring. So what was it? It was the sigma times the square root of minus eta mu nu dx mu d sigma dx nu d sigma. And then from here we derive the fact that the classical trajectory for the particle is the straight line, not surprisingly. Now we want to add a charge. So imagine the particle as a charge, and there is some background electromagnetic field in here. So it's propagating this background electromagnetic field, and I assume you have seen the fact that electromagnetic field can be described by a potential, by a 4 vector A mu, in terms of which the field strength, the electromagnetic field strength F mu nu is given by d mu A mu minus d mu A mu. And then this field strength is related to the electric and the magnetic field in the following way. So F0I is equal to minus EI, where it is the electric field, and Fij is equal to epsilon ijk bk, where epsilon is the fully anti-symmetric metric, the relativity, not metric, the fully anti-symmetric symbol, a tensor, in the spatial coordinates. And B is the magnetic field. So we have this relation, and that A mu field is just the collection of the electrostatic potential and the vector potential that sometimes, I guess, when we are younger, we study them as two separate things. But then in the Lorentz, when we write a Lorentz invariant formulation of Maxwell theory, then they will combine into the full A mu. So A mu with upper indices is composed of phi, the electrostatic potential, and the vector potential. Okay, so we have this background field, say some electric field. It can be localized, doesn't have to, but say we have some electric field in this region. And then this particle is moving through the electric field, and therefore its motion will be modified. It will experience some force. And we want to write some action that describes this motion. Okay. So basically, here I'm going to write the simplest possible term that we can write, add to this action. First of all, I'm going to put a factor of m here, the mass of the particle. It doesn't change the equation of motion for a free particle if I multiply this action by any number. So I can, this doesn't make any difference here. But then when I add an additional term, then it does make a difference. Then it plays the role of the mass of the particle. And I'm putting it here because eventually it will give me the right equation of motion with mass sitting at the right place. Okay, so now what do I want to add? We want to write the action. The action is an integral over the trajectory, so integral over sigma. It will be an integral of the local Lagrangian. And of course it has to vanish if the charge is 0, so I put Q here. It has to be proportional, it has to vanish when the vector potential or the field vanishes. So there has to be at least one factor of A mu sitting there. If I'm in weak field, if the electromagnetic field is not very strong, we will be dominated by the lowest power of this A mu, right? So if this A mu or this if F mu is small, we want to keep the lowest order term in that. And if I'm also imagining that the wavelengths or the characteristic size of the variation of this field is very large. So we want, what does that mean? That means that if I consider derivatives of this A, that is some length scale divided by A, and I want to take this length scale to be large. well, these derivatives of A in particular appear in the field extent. So when I say the fields are small, that will also consistent with this assumption that the length scale of the variation is small. So now what does it imply? When I take derivatives, I'm essentially dividing by the length scale over which the field appears. So if the length scale of variations is small, the field is changing very slowly, I want to have as few number of derivatives as possible. And the least number of derivatives that I can put here is 0. So what I can write is that so there is a factor a mu, and the object that I can put here using the parameters of using the trajectory of the particle is dx mu by d sigma. So this is the proposal for the coupling of the charged particle to the background electromagnetic field. Now I want to see, let me write it as big X. We want to see what equation of motion do we derive by using this action. Okay, so we do the usual thing. We do a variation of the action. We take x going to x plus delta x, or x mu going to x mu plus delta x mu, and ask how the action change under this variation. The assumption is that delta x mu vanishes at the end points, so at this point and that. That allows us to do integration by parts, for instance. So this delta s, the first term is what we already had before. There is minus eta mu nu dx mu d sigma d delta x mu d sigma divided by the square root of eta mu. That means different indices here. Alpha d sigma x beta d sigma, and then here we have minus q integral. So there are two terms. There is one which is delta x mu d delta x mu d sigma times a mu, and then there is a second term which is d x mu d sigma, and then it comes from the fact that a mu itself is evaluated on the trajectory of the particle. So then I have d mu a mu delta x nu. So as before, what I do is that I do some partial integrations to write this whole action in terms of this whole variation in terms of delta x mu times something, and that something is the equation of motion. That is the thing that has to vanish when the equations of motions are satisfied, or has to vanish on shell, as we say in particle physics. Yes?
When we take the relation for last term, we take first for x mu. So, because it's the same index as mu. But when we take it for mu, we change the index. But we should do the same definition for the same variable.
But the index of mu is the same, right? So I'm just saying. So let's look here. So I have a mu of x. Of course, this is the full 4 vector, right? Now, what is the variation of this delta a mu of x? That is a mu of x plus delta x minus a mu of x, right? And this is if in the limit that delta x goes to 0, a linear order in delta x, this is just delta x nu d mu times a mu. So that's what I have done. Right? Alright, so now let's do partial integrations. But I just write the equation of motion direct. So I have m. So here I should do one partial integration, so the minus sign cancels. M d by d sigma of eta mu nu dx nu d tau. So we remember that this factor is nothing but d tau, d sigma. And that's how this derivative with respect to sigma becomes a derivative with respect to tau. Okay, so this is this term. Here I have to do a partial integration, so the minus sign will cancel. So I get q times d a mu d sigma, and here I will get minus dx mu d sigma d mu a mu equals 0. Now one thing that I can do is to multiply the whole equation by d sigma d tau, so that these derivatives become tau derivative just by the chain rule. So this, I just do this tau, and these two become tau. And then we can write d mu, dA mu d tau. We can again use the chain rule. So a mu is evaluated along the trajectory. But this is really a mu of x of tau. So this derivative is equal to dx mu d tau d mu a mu. So what does it give me? It tells me that m times, or let me just, m times d by d squared x, okay, sorry, I introduced this x mu with lower indices, which is just a tau mu nu times x nu but with upper indices. And then these terms I can take them to the right hand side and use this relation for dA by d tau. So what I get is q dx nu d tau times d mu a mu minus d mu a mu and this is nothing but Q times U nu times F mu nu. Any questions about the derivation? Yes.
In writing direction, we put dx mu, d sigma, but we didn't put, for example, just x mu. Is there a reason why do we put
Here? Well, I want my action to be, I mean, what would be the alternative? Tell me the alternative.
just x mu, for example.
So for instance, d sigma times x mu times a mu. This is not a good alternative because it's not invariant on the shifting the origin. So if I just take the origin of the coordinates and put it somewhere else, right, that will introduce a non-zero change in this action, while physically nothing happened. So the rules for writing the action was that we want to write an action which is invariant on the Poincaré transformation. So this one doesn't satisfy. Okay, so other questions? No. So this equation can be written in a more familiar way if we go to a rest frame, or not rest frame, but if we go to a small velocity, then perhaps it looks more familiar. It turns into the Lorentz force that we write. And if we use the relation between F mu nu and the electric and magnetic field. So when velocity v is much less than 1, then this equation just becomes m times dv dt, which is ma equals the force. It becomes equal to the Lorentz force, v, the vector. So this is just what I get from the left hand side. On the right hand side, I will have from the zeroth component of this u, I will get the electric field. So there will be E. And then from the I component, when mu is I will get the magnetic force, V cross B. Of course, this equation is relativistic, so you can write the exact relativistic version of the Lorentz force. But in the limit, it tells into this expression. Questions?
The assumptions that we make to introduce the extra term is that our field change slowly.
Mm-hmm.
So that's all. But now we can use that equation for configuration where our field change rapidly or?
Well, if the variations of the field are very large, then in principle you could imagine that there are other terms, other corrections in this equation that would become equally important. So, this is a good description as long as you are talking about the fields which vary slowly. Now you can, one exercise is to try to write down higher derivative corrections to this equation and derive to this action and derive the corresponding corrections to the Lorentz force. So see what could you add to this action which satisfy all of the symmetry requirements. So there are a lot of terms, and then there would be subleading in the limit of the small derivatives. Then you can see that as you go to higher derivatives, those terms become important. Usually, so for instance, in 4D we are talking about we are organizing these terms when we talk about various fields or interactions between different fields or particles and fields. We organize these terms in some derivative expansion, and this derivative expansion usually has a parameter in it. So there is a parameter that controls the expansion. So for instance, here if you want to add a higher derivative term to this action, that will come with a parameter which is dimension full. And then the resulting equation will tell you that that force term breaks down or becomes incorrect once you look at the gradients which are of order of that dimension that you are putting for higher derivative correction. So for instance, those higher derivative corrections know about the internal structure of this particle. This might not, in reality we are describing this charged particle might have some internal structure, therefore it might have some dipole moment. So here we have just written the coupling of the charge of the particle, the monopole moment of the particle to the background field. But if it has some internal structure, it can have electric or magnetic dipoles. Those terms we also can also be described in this language. There will be high derivative corrections to this action that depend on the dipole moment of the particle or higher moments of the charge distribution of your particle. And then this force law will be valid as long as the wavelengths of the variations of your field is much larger than the internal structure, the size of your particle. Once the variations become very small, then you cannot ignore those corrections. Even if the variations have long wavelengths, those will be corrections that you can in principle include and measure if you have enough precision. Yes.
One question, if he has.
Do you have?
We at first try to minimize or extremize the distance between 2 points.
Mm-hmm.
We are trying to write the first term.
Yeah.
This additional term has any meaning in terms of extremizing the distance, or like now we are kind of writing the standard Lagrangian, like energy density in terms of dimensions. We kind of jumped from extremizing the distance to the energy density dimension or something like that.
Yeah, I'm not sure if I have some very simple interpretation. Also, when you write the action for the, like a field, the action itself is not, so you are integrating over the Lagrangian. That's not the energy density, right? But it's the invariant quantity that you can write. Lorentz invariant quantity that you can write. So here is the same thing. This time it's kind of reminiscent of the potential difference that you have between 2 points. Like if you go to the, is it that? It's not even that actually. No, I don't know. Like this is more or less like the bomb, something that gives you the phase if you consider the, I don't know if it is a simpler explanation or interpretation or it's more complicated, but if you imagine in quantum mechanics, that's the phase that you get if you have a charged particle propagating in the background field. Okay. Yeah, one thing about the writing the action. So far we were writing, how did we write the action? We wrote it as some Lagrangian density integrated over the trajectory of the particle. So this was a one-dimensional object, a one-dimensional word line, and therefore the action was a one-dimensional integral of the Lagrangian density. Now, you could ask, for instance, say if the particle was not charged, this time was just the Lorentzian length of the curve that connects the 2 points, right? You could ask what the other possibilities for the action are. So you could try to come up with other alternatives. So for instance, in the case of a free particle, you could just take the length and square it and define the action as the square of the Lorentzian length. That would still be extremized by the straight line, right? If there was no force here, then once you extremize the length, you have also extremized length squared or any function of the length. So you could imagine writing actions which are more complicated. It's not just the integral over the word line, but say the square of this quantity. But you can see, this is already one simple example of some more general rule for writing actions. We usually write action as the integral over the, here it was a word line, in the case of field theory, it's the integral over the spacetime. So it's a single integral over the dimensions that whatever field that we have lives on. You can already see in this simple example that if you consider something more complicated, like say the square of that, then the force laws or the equations of motion that you are going to get is going to be non-local. So it will depend, for instance, the force that particle feels will depend on the full history. And indeed, there is a general principle called cluster decomposition principle. You might have heard about it in QFD course. Cluster decomposition principle is basically the principle that if you perform experiments at faraway points and take these two experiments to infinity, the results of the two should not affect each other. So that's the physical principle that we impose on the theories that we work with. That principle implies that the action that we write has to have this structure. So it has to be written as integral over the dimensions that we have a single integral over the dimensions of a local Lagrangian density, which is what this is. And if I wrote length squared, then it wouldn't be. So for instance, we can imagine a very simple scenario. Say you have a localized electric field here, and then take the action to be Lorentzian length squared. This term of the action, take it to be some function of the Lorentzian length instead of, as opposed to what I wrote. Then you will see that depending on what function you use, then the trajectory of the particle will change. And it will also depend on the full history. So if you go back to here and try to evaluate, then the trajectory will be something different. So some, I guess, nice toy example of how you can break cluster decomposition. Okay, so this was on this side. One thing that I should say here is that you can derive, now given this, so this, don't break cluster decomposition. Given this point particle action, or this coupling between our charged particle and electromagnetic field, another thing that you can do is that to derive the source term for the Maxwell equation, right? So if you have a charged particle that moves in a space-time, so we have this charged particle moving, that is of course a source for electromagnetic field. So not only it is affected by the existing background field, it will also produce an electromagnetic field. And how do we describe that? We describe this by the sources that sit in the right-hand side of Maxwell equation. So in this language, the Maxwell equation is d mu f mu nu equals to some j nu, where j nu is the electromagnetic, is the electric current. Now, for instance, we can ask what is the electric current corresponding to this charge particle, and so how do we derive it? We derive it by using the following fact, that this equation for these Maxwell equations can be derived again by writing an action for the electromagnetic field, for the electromagnetic potential A mu. So what is that action? That action is just the Maxwell action. So now we are talking about the field which lives on the space-time. So this action will be an integral over the full space-time times 1 minus 1 over 4 f mu nu plus a coupling of A mu to the sources. And this comes with a negative sign. So if I vary this action, so this is an action written for the A mu field. If I vary this action with respect to A mu, then the resulting equation of motion will be that. Now, given a trajectory for this charged particle, then, and this coupling between the point charge and the background field, we can evaluate what would be the source term that sits in this action. Now, of course, this is something that is defined on the word line. So in order to promote it into something that lives in the space-time, we should introduce some delta function. So if I write an integral over the whole space, and this source will be a source which is localized on the trajectory of the particle. So it will be there will be a three-dimensional delta function that localizes this for the integral over the trajectory. And I won't derive it, but the derivation is given in the notes. You can see that the current is given by Q times dx mu dt or dx0, let's go t, times delta 3 of x mu minus x mu of t. Sorry, not xi minus xi of t. So now big X corresponds to the trajectory of the particle. So I have some particle which moves on this trajectory xi of t. And little x is the variable of integration here. So if I have a fixed trajectory for this charged particle, then I will have the following current, electric current, that will be the source term in my Maxwell theory, and I can derive it by playing with this interaction term that I have. Yes?
In doing this, are we combining the two actions into a single action and introduce the Dirac delta functions to write it? So after doing that, can we obtain this expression should be the current, or are we putting it by hand that this should be the current that gives rise?
No, if you just, this will be just I mean, if I, this term is irrelevant because we are interested in the coupling to A mu. So I have this point particle action, I have electromagnetic, the Maxwell action. Now I'm saying that if we take this term, which is defined on the word line, we can promote it into an action which is defined on the full space-time, and then if you compare it to this expression, you can see what is the corresponding J.
So we just put the free Maxwell action,
yeah,
and I see that it corresponds to the J.
I guess I should say this is J mu for a charged point particle.
And we didn't introduce the dipole or internal structure terms.
No, we didn't. In principle, yeah. Well, those would introduce sources which look differently. They wouldn't be. So if I put the dipole moment here, if I consider the internal structure, then that source is not going to be an electric current. It will be a dipole term that will appear on the right hand side of Maxwell equation. If there is no other question, I move to the discussion of symmetries and Noether theorem. Or symmetries and conservation laws. So the idea is that the symmetries, or whatever theory that we have, they have consequences. They lead to conservation laws. You have probably seen in classical dynamics that the time translations lead to energy conservation. Space translations lead to momentum conservation, and rotation symmetry leads to angular momentum conservation. So now we are going to study the same connection between symmetries and conservation laws in the context of field theory, and talk about Noether theorem, which gives us basically a machinery to start from symmetries and go and derive the conserved quantity. So now I'm going to consider some general action for a field phi, but this field can be a collection of fields. Doesn't have to be a single field. Doesn't have to be just a scalar field. Phi can, for instance, be this A mu. Now this is just an abstract notation. There is some. We know that if we have a field theory, we describe it by an action which is written as the space-time integral of a Lagrangian density L of phi. And we want to imagine a situation in which this action has a symmetry. Well, what do we mean by the symmetry of the action? What we mean is that if we transform this field phi to phi plus some delta phi, or delta s for symmetry, then there will be a variation of the action. So if we do this variation of the field in this action and we linearize in delta s phi, then delta s of the action is going to be integral d4x times d mu of some lambda mu, some total derivative. So this is something that I call a total derivative, a total divergence derivative. So if I have a transformation under which the change in the action is a total derivative, I call that transformation a symmetry transformation. So far, just the definition, what I mean by symmetry transformation. We'll see some examples very soon. Now, if such a symmetry transformation exists, then there is another theorem that tells us how to derive a conservation law. So whenever we have something like that, there will be an associated conservation law. How do we derive that conservation law? It's very simple. What we do is that we modify that transformation, symmetry transformation, by multiplying this change, this variation, by some epsilon of x. Where epsilon is some arbitrary function of a space-time. So epsilon is an arbitrary function of a space-time. Eventually, we want to take it to be something localized around any point that we are interested in. But it's arbitrary. So now, what is the change of the action? So if I look at delta S, so this is delta, how do we call it? This is delta epsilon of S. So how should it look like? If epsilon was a constant, if it didn't vary, then the result would be a total derivative, right? So that's just the previous one. If epsilon was a constant, we would get a total derivative. Now that epsilon is not a constant, then the result might be different from a total derivative, but only by a term that has the derivative of this epsilon parameter. And then by Lorentz symmetry, that derivative has to be contracted with something, which I call J mu. And then in addition, we can have total derivative. So this is the most general answer that we can get if we follow this procedure. Note that it's linear in epsilon because we are linearizing in this transformation. So also here we were linearizing. So here I'm also linearizing. So the result is by construction linear in epsilon. It has to vanish when epsilon is a constant, therefore it has to have this structure. Okay, now what we want to do is to take this epsilon to be localized around some point. Some arbitrary function, but such that it vanishes at infinity. Now, if I make that extra assumption, so if epsilon of x going to infinity is equal to 0, then this operation is just what we normally do when we do a variation of the action. So it's just a particular form of variation. So remember when we did the variation of the point particle action, we took x mu and we changed it by some delta x mu with the only condition that delta x mu was arbitrary, except that it would vanish at the endpoints. Now, when we talk about fields, the same criterion is that we have some boundaries. It can be infinity here. So here I assume that it goes all the way to infinity. We have some boundaries. We do an arbitrary variation of the field, except that we require that variation vanishes at the boundaries. And when we do that, what we obtain is the equations of motion. So now every total derivative becomes irrelevant because the total derivative terms reduce to the boundary terms where epsilon is 0. So I can freely do integration by parts, and my delta epsilon s is given by minus d for x epsilon d mu j mu. Now, if the equations of motion, are satisfied, then the variations of the action has to vanish under an arbitrary variation. What does it mean? It means that this d mu j mu has to vanish when the equations of motion are satisfied. So what we learn is that d mu j mu is equal to 0 on shell. By on shell, I mean when the equations of motion are satisfied. Yeah.
That one doesn't mean that epsilon equals 0. That delta is equal to 0 at the second line, because
here.
No, the second line, the first two bars. When epsilon x goes to infinity, equal to 0.
Right.
It's delta s what is equal to 0, or epsilon itself equal to 0.
Here.
Yeah.
Oh, I'm saying that this epsilon was an arbitrary parameter, right? So what I'm doing is that let's take epsilon as a function of x, right? So I'm just assuming that this epsilon is localized. It vanishes at infinity.
I see.
Now I'm saying that when I make this assumption, this is one particular variations of the action. We know that the variations of the action around the solutions of the equation of motion have to vanish because the action is extremized on the equations of motion. So linear variations of the action vanish. Okay, so this is another theorem. We derive the conserved current associated to that symmetry. Now this looks very abstract. We can probably understand it better or more explicitly at the level of concrete examples. See that it actually works.
Why not epsilon on shell equal to 0 maybe?
Oh, epsilon is an arbitrary parameter, right? So it's very similar to when we derive the equations of motion. Remember when we said I want to derive the equation of motion for x mu when I had a point particle action. I said that let's take x mu go to x mu plus delta x mu. Delta x mu was just an arbitrary variation, but a small variation. What I required was that for any delta x mu, the variation is equal to 0, and that gives me the equation of motion. Now here, I'm doing a similar thing. I'm taking this epsilon to be an arbitrary parameter, and the statement is that as long as this arbitrary parameter vanishes at the boundaries, then the variation of the action, linearized variation of the action, has to vanish on the equations of motion, on the solutions of the equations of motion.
Okay, I see. So on shell doesn't mean the boundaries. It means the equation of motion for
Yes.
the whole trajectory.
Yes, yes. We are gonna see it in some explicit examples. probably makes it more transparent. Okay, so the simplest example is let's consider some scalar field, a free scalar field. So again, S of phi, but now this phi is not an abstract notation; it's really a free scalar field whose action is d phi squared. Free massless scalar. And d phi squared is the shorthand notation for eta mu d mu phi d mu phi. Okay, so let's see what are the symmetries of this action. So one symmetry of this action is if I shift phi by a constant, say by 1. Or maybe we want it to be a small variation, so let's call it epsilon, but epsilon is a constant. So if I do that, then maybe epsilon is not a good notation because then it becomes, let's call it C. C is a constant. And then delta C of the action is equal to what? If I shift phi by a constant, the variation of the action under this is 0 because I have derivatives of phi. So this is trivially a symmetry. So this is a case in which this total derivative is actually 0. This lambda mu that I introduced there is exactly 0. So delta C of S is 0. I'm satisfying the condition for having a symmetry. I have an action that under this transformation changes by a total derivative, in this case is 0. And now we can derive the associated current, conserved current, to this symmetry. So how do we derive it? We follow that prescription. We take phi going to phi plus epsilon of x, some arbitrary function of x, times whatever parameter that we have. Now as you see, this is kind of redundant because c is just a constant. So I can just absorb it into my epsilon, redefine my epsilon. Keeping in mind that epsilon is an infinitesimal, so I'm only keeping to varying into linear order in epsilon. So let me just drop this c, the constant. So now we look at the variation of the action with this change. Linear order in epsilon. So what do we get? I have to plug it in these two terms, these two phi's, and linearize, so I get a factor of 2, which cancels 1/2. So I get minus d4x eta mu nu d mu phi d nu epsilon. Or let me call it d mu epsilon d mu phi. Let me put this minus in here. Now we can compare this equation with that equation. And so as we see, it's exactly, has the exact structure that we expected. That it's going to be proportional to derivatives of epsilon. And what multiplies derivative of the epsilon, we decided to call that J mu. So now here J mu is nothing but minus eta mu nu d nu phi. And what is the property of this J mu? It is supposed to be conserved when the equations of motions are satisfied. So let's see if that is true. And it is true, obviously, because d mu, J mu is equal to minus eta mu nu d nu phi, which is also called box phi. And indeed, this is equal to 0 on shell. This is just the equation of motion that we would derive from the action. A less trivial symmetry of this action is if we do a space-time translation. It is invariant under space-time translation, which is the following: a uniform space-time translation whose parameter I call a mu. So if I take phi to phi plus a mu d mu phi, where a mu is just a constant 4 vector. Then again, the variation of the action is going to be a total derivative. So let's see what is this variation. Again, what I do is I plug this in here, I linearize in A. These two give the same contribution because of the symmetry of eta mu nu. So the answer is d4x eta mu nu d mu phi d nu of a alpha d alpha phi. Now since A is constant, I can take it out of the derivative. So this is equal to d4x a alpha eta mu nu d mu phi d alpha d mu phi. But this is equal to minus 1/2 a alpha the alpha of eta mu nu d mu phi. Let's write this just as d phi squared. So we are not used to the notation. Because of the symmetry of this eta mu nu. And again, since A is constant, I can take it inside, so I get minus 1/2 d4x d alpha of a alpha d phi squared. Now the variation of the action under this translation, uniform space-time translation, is not 0, but it is a total derivative. So this lambda here is now going to be minus 1/2 a alpha times d phi squared. So again, this is a symmetry transformation. It satisfies the definition of a symmetry transformation. And there is an associated conserved current, and the conserved current associated to space-time translations is called the energy momentum tensor. So how do we derive that? Again, we follow the Noether's procedure. We promote the symmetry transformation into a local variation by multiplying by some epsilon of x. So we say phi goes to phi plus epsilon of x a mu d mu phi. Now again, these a mu's are 4 constants. I can a little bit simplify the notation by absorbing it into epsilon, introduce a 4 vector epsilon, some epsilon mu of x. And then ask what is the variation of the action when this epsilon mu depends on x. So I look at delta epsilon of x. So follow essentially the same procedure, except that I keep in mind that this epsilon is not constant. So delta epsilon of s is integral d4x. Now I just raise and lower the indices with eta mu nu. So I have d mu of epsilon nu d nu phi. This is there are 2 contributions, one when the derivative acts on epsilon, one when it acts on phi. So I will have d mu epsilon nu d mu phi and then I have epsilon nu d mu phi d mu phi. Now this term can be written as 1/2 d mu d phi squared therefore what I get, I can write this whole thing as the total derivative plus this d mu acting on epsilon nu. Sorry, minus. So what I get is integral d4x d mu epsilon nu times d mu phi minus 1/2 epsilon delta mu nu times d phi squared plus the total derivative. So now we expect to have in four space-time dimensions, we expect to have 4 conserved quantities rather than 1, because our symmetry transformation had 4 parameters. So for any component of this A, I will get 1 conservation law. Or we can put all of them together into 1 conservation law, not for a current, not for a conserved current, but for a conserved tensor, which is the energy momentum tensor, which is this object. So this is T mu nu, the energy momentum tensor, which, so you should think about this mu index that is contracted with the index of epsilon as a label. So we have 4 translations, 4 space-time translations, which correspond to the 4 components of this A mu. For any of them, there is a conserved quantity. So this mu that is contracted with the index of this epsilon, now remember epsilon is just replacing A. So this mu index is just a label of those 4 transformations, and this mu is the analog of the mu in our current. So it's the one that the index that is contracted with the derivative of our transformation parameter. So what do we expect? We expect that d mu of t mu nu is equal to 0. Again, unsure. Now, is it true? We can check it. We can check it explicitly. So let's check it to make sure that it is indeed the case. If I calculate d mu of t mu nu, this is equal to box phi times d nu phi plus d mu phi d mu d nu phi minus, when the derivative acts on this, first of mu becomes mu because of the delta mu nu, and then it can act on both of these two. So what it gives me is, so that is a factor of 2 that cancels this and gives me d mu phi, d mu phi. Well, let me call it something else. These are the domain indices, so I can call it whatever. Equals 0. Sorry, we want to see that. So it's equal to this. But these two terms are the same because the mu index here and alpha index there are summed over. So these two terms are the same. So I end up with d nu phi box phi. But on the equations of motion of this action, box phi is equal to 0. So this is equal to 0 on shell. As expected. One exercise that you can do is to add a mass term to this scalar field and follow the same procedure to find the stress energy tensor for a massive scalar. By the way, this energy momentum tensor, it is also called a stress energy tensor. These are just two names for the same thing. But the conservation laws that we have, we essentially have one conservation law for every index here, and those are energy and momentum conservations. Any question? So I'll keep calling them conservation laws without saying why. So you can introduce conserved charges when you have conserved current. That's why. That's the reason why they're called conservation laws. So when you have d mu j mu equal to 0, then we can introduce a conserved charge. And this expression is a local, the expression of the local conservation of that charge. It tells us that that charge is the total amount of charge is conserved. It can just move from one point to the other. So this equation just tells us, if we write it, if we break Lorentz, the way to think about this equation is to write it as a density. So write this J mu as a density and a current and the space current. And then that equation is the statement that rho dot is equal to minus divergence of J. The density of charge is changing only if there is a divergence of the current. Now we can introduce a global charge by integrating that zeros component over the whole space. So d3x j0, which is rho. And this total charge is conserved because of our conservation law. So if I want to calculate d by dt of q, that will be equal to d3x. I take the time derivative inside the integral, it becomes a partial time derivative. It becomes d0 of j0, partial with respect to time. And then using that equation, this is equal to d3x times di jr with a negative sign. Which reduces to the boundary term. So in particular, if I'm integrating over the whole space, which is what I meant by this, then this integral reduces to the flux of the charge at infinity on the sky r to infinity. So we have some d s I j I. In particular, if everything vanishes at infinity, if the fields are all vanishing at infinity, there is no flux at infinity, then our charge will be conserved. Alright, so we'll stop here. Next week we'll have one session.